Welcome to Amazing World Channel.
It is one of cosmology's more perplexing problems that up to 90% of the ordinary matter in the universe appears to have gone missing. Now astronomers have detected about half of this missing content for the first time, in a discovery that could resolve a long-standing paradox. The conundrum first arose from measurements of radiation left over from the Big Bang, which allowed scientists to calculate how much matter there is in the universe and what form it takes. This showed that about 5% of the mass in the universe comes in the form of ordinary matter, with the rest being accounted for by dark matter and dark energy. Dark matter has never been directly observed, and the nature of dark energy is almost completely mysterious, but even tracking down the 5% of ordinary stuff has proved more complicated than expected. When scientists have counted up all the observable objects in the sky, stars, planets, galaxies and so on, this only seems to account for between a tenth and a fifth of what ought to be out there. The deficit is known as the missing baryon problem, baryons being ordinary subatomic particles like protons and neutrons. Richard Ellis, a professor of astrophysics at the University College London, said people agree that there's a lot missing, raising the question where is it the distribution of galaxies in the universe follows a web-like pattern, and scientists have speculated that the missing baryons could be floating in diffuse gaseous filaments and sheets linking the galaxy clusters in the cosmic web. Theoretical calculations suggest these gaseous threads, known as the warm-hot intergalactic medium, or the WIM, ought to be around 1,000,000 degrees Celsius. A mist of gas at this temperature is too cold to emit X-rays that could be spotted by ordinary telescopes from the Earth, but not cold enough to absorb significant amounts of light passing through it. The trouble is, it's in this unusual temperature regime where we can't see it, said Ellis. Now two separate teams of scientists, one at the University of Edinburgh, the other at the Institute of Space Astrophysics in Orsay, France, have produced compelling indirect evidence for the WIM. Both teams relied on the fact that when radiation travels through a hot gas, it is scattered, meaning that the WIM ought to appear as a dim outline in the cosmic microwave background. The scientists overlaid observations of the cosmic background radiation made by the Planck Space Observatory and their most detailed three-dimensional map of the cosmic web created by the Sloan Digital Sky Survey (SDSS). They hypothesized that, if there were gas threads linking galaxy clusters, these should show up in the Planck data. The Edinburgh team found the regions between galaxies appeared to be about 6 times as dense as the surrounding bits of space, and when summed up, these gaseous threads could amount to about 30% of the ordinary matter in the universe. The French team's calculation came out at slightly less than this, but the numbers are consistent. Ellis, who was not involved in either project, describes the findings as inspirational. These two papers have been very prominently discussed, and people are excited, he added. The WIM is out there. The initial measurements still do not account for all the ordinary matter, and some believe the remaining portion could be made up by exotic unobserved objects such as black holes or dark stars. Cosmologists are also still yet to discover the nature of dark matter, which makes up even more of the universe.